Pulse width modulation, or pulse duration modulation, is a modulation technique that controls the width of the pulse, formerly the pulse duration, based on modulator signal information. Although this modulation technique can be used to encode information for transmission, its main use is to allow the control of the power supplied to electrical devices, especially to inertial loads such as motors. In addition, PWM is one of the two principal algorithms used in photovoltaic solar battery chargers, the other being MPPT. The average value of voltage fed to the load is controlled by turning the switch between supply and load on and off at a fast pace. The longer the switch is on compared to the off periods, the higher the power supplied to the load. The PWM switching frequency has to be much faster than what would affect the load, which is to say the device that uses the power. Typically switching has to be done several times a minute in an electric stove, 120 Hz in a lamp dimmer, from few kilohertz to tens of kilohertz for a motor drive, and well into the tens or hundreds of kilohertz in audio amplifiers and computer power supplies. The term duty cycle describes the proportion of on time to the regular interval or period of time. A low duty cycle corresponds to low power, because the power is off for most of the time. Duty cycle is expressed in %, 100% being fully on. The main advantage of PWM is that power loss in the switching devices is very low. When a switch is off there is practically no current, and when it is on, there is almost no voltage drop across the switch. Power loss, being the product of voltage and current, is thus in both cases close to zero. PWM also works well with digital controls, which, because of their on-off nature, can easily set the needed duty cycle. PWM has also been used in certain communication systems where its duty cycle has been used to convey information over a communications channel. History: in the past, when only partial power was needed, a rheostat connected in series with the motor adjusted the amount of current flowing through the motor, but also wasted power as heat in the resistor element. It was an inefficient scheme, but tolerable because the total power was low. This was one of several methods of controlling power. There were some still in use such as variable auto-transformers, including the trademarked Autrastat for theatrical lighting, and the Variac, for general AC power adjustment. These were quite efficient, but also relatively costly. For about a century, some variable-speed electric motors have had decent efficiency, but they were somewhat more complex than constant-speed motors, and sometimes required bulky external electrical apparatus, such as a bank of variable power resistors or rotating converters such as Ward-Leonard drive. However, in addition to motor drives for fans, pumps and robotic servos, there was a great need for compact and low-cost means for applying adjustable power for many devices, such as electric stoves and lamp dimmers. One early application of PWM was in the Sinclair X10, a tenor W audio amplifier available in kit form in the 1960s. At around the same time PWM started to be used in AC motor control. Principle: pulse width modulation uses a rectangular pulse wave whose pulse width is modulated, resulting in the variation of the average value of the waveform. If we consider a pulse waveform, with period, low value, a high value and a duty cycle d, the average value of the waveform is given by. As is a pulse wave, its value is 4 and 4. The above expression then becomes. This latter expression can be fairly simplified in many cases, whereas from this, it is obvious that the average value of the signal is directly dependent on the duty cycle d. The simplest way to generate a PWM signal is the intersective method, which requires only a sawtooth or a triangle waveform and a comparator. When the value of the reference signal is more than the modulation waveform, the PWM signal is in the high state, otherwise it is in the low state. Delta. In the use of delta modulation for PWM control, the output signal is integrated, and the result is compared with limits, which correspond to a reference signal offset by a constant. Every time the integral of the output signal reaches one of the limits, the PWM signal changes state. Figure 3. Delta sigma. In delta sigma modulation as a PWM control method, the output signal is subtracted from a reference signal to form an error signal. This error is integrated, and when the integral of the error exceeds the limits, the output changes state. Figure 4. Space vector modulation. Space vector modulation is a PWM control algorithm for multi-phase AC generation, in which the reference signal is sampled regularly. After each sample, non-zero active switching vectors adjacent to the reference vector and one or more of the zero switching vectors are selected for the appropriate fraction of the sampling period in order to synthesize the reference signal as the average of the used vectors. Direct torque control. Direct torque control is a method used to control AC motors. It is closely related with the delta modulation. Motor torque and magnetic flux are estimated, and these are controlled to stay within their hysteresis bands by turning on new combination of the device's semiconductor switches each time either of the signal tries to deviate out of the band. Time proportioning. Many digital circuits can generate PWM signals. They normally use a counter that increments periodically and is reset at the end of every period of the PWM. When the counter value is more than the reference value, the PWM output changes state from high to low. This technique is referred to as time proportioning, particularly as time proportioning controller euro, which proportion of a fixed cycle time is spent in the high state. The incremented and periodically reset counter is the discrete version of the intersecting method sawtooth. The analog comparator of the intersecting method becomes a simple integer comparison between the current counter value and a digital reference value. The duty cycle can only be varied in discrete steps, as a function of the counter resolution. However, a high-resolution counter can provide quite satisfactory performance. Types. 3 types of pulse width modulation are possible. The pulse center may be fixed in the center of the time window and both edges of the pulse moved to compress or expand the width. The lead edge can be held at the lead edge of the window and the tail edge modulated. The tail edge can be fixed and the lead edge modulated. Spectrum. The resulting spectra are similar, and each contains a DC component, a base sideband containing the modulating signal and phase-modulated carriers at each harmonic of the frequency of the pulse. The amplitudes of the harmonic groups are restricted by O envelope and extend to infinity. The infinite bandwidth is caused by the nonlinear operation of the pulse width modulator. In consequence, a digital PWM suffers from aliasing distortion that significantly reduces its applicability for modern communications system. By limiting the bandwidth of the PWM kernel, aliasing effects can be avoided. On the contrary, the delta modulation is a random process that produces continuous spectrum without distinct harmonics. PWM sampling theorem. The process of PWM conversion is nonlinear, and it is generally supposed that low-pass filter signal recovery is imperfect for PWM. The PWM sampling theorem shows that PWM conversion can be perfect. The theorem states that any band-limited baseband signal with an A plus or minus 0.637 can be represented by a pulse width modulation waveform with unit amplitude. The number of pulses in the waveform is equal to the number of Nyquist samples, and the peak constraint is independent of whether the waveform is 2-level or 3-level. Applications. Servos. PWM is used to control servo mechanisms, see servo control. Telecommunications. In telecommunications, PWM is a form of signal modulation where the widths of the pulses correspond to specific data values encoded at one end and decoded at the other. Pulses of various lengths will be sent at regular intervals. Clock. PWM signal. Data 01240410. The inclusion of a clock signal is not necessary, as the leading edge of the data signal can be used as the clock if a small offset is added to the data value in order to avoid a data value with a zero-length pulse. PWM signal. Data 01240410. Power delivery. PWM can be used to control the amount of power delivered to a load without incurring the losses that would result from linear power delivery by resistive means. Potential drawbacks to this technique are the pulsations defined by the duty cycle, switching frequency and properties of the load. with a sufficiently high switching frequency and, when necessary, using additional passive electronic filters, the pulse train can be smoothed and average analog waveform recovered. High-frequency PWM power control systems are easily realizable with semiconductor switches. As explained above, almost no power is dissipated by the switch in either on or off state. However, during the transitions between on and off states, both voltage and current are non-zero and thus power is dissipated in the switches. By quickly changing the state between fully on and fully off, the power dissipation in the switches can be quite low compared to the power being delivered to the load. Modern semiconductor switches such as MOSFETs or insulated gate bipolar transistors are well-suited components for high-efficiency controllers. Frequency converters used to control AC motors may have efficiencies exceeding 98%. Switching power supplies have lower efficiency due to low output voltage levels, but still more than 70–80% efficiency can be achieved. Variable speed fan controllers for computers usually use PWM, as it is far more efficient when compared to a potentiometer or rheostat. Light dimmers for home use employ a specific type of PWM control. Home-use light dimmers typically include electronic circuitry which suppresses current flow during defined portions of each cycle of the AC line voltage. Adjusting the brightness of light emitted by a light source is then merely a matter of setting at what voltage in the AC half-cycle the dimmer begins to provide electrical current to the light source. In this case, the PWM duty cycle is the ratio of the conduction time to the duration of a half AC cycle defined by the frequency of the AC line voltage. These rather simple types of dimmers can be effectively used with inert light sources such as incandescent lamps, for example, for which the additional modulation in supplied electrical energy which is caused by the dimmer causes only negligible additional fluctuations in the emitted light. Some other types of light sources such as light-emitting diodes, however, turn on and off extremely rapidly and would perceivably flicker if supplied with low-frequency drive voltages. Perceivable flicker effects from such rapid response light sources can be reduced by increasing the PWM frequency. If the light fluctuations are sufficiently rapid, the human visual system can no longer resolve them and the eye perceives the time average intensity without flicker. In electric cookers, continuously variable power is applied to the heating elements such as the hob or the grill using a device known as a simmerstat. This consists of a thermal oscillator running at approximately 2 cycles per minute and the mechanism varies the duty cycle according to the knob setting. The thermal time constant of the heating elements is several minutes, so that the temperature fluctuations are too small to matter in practice. Voltage regulation. PWM is also used in efficient voltage regulators. By switching voltage to the load with the appropriate duty cycle, the output will approximate a voltage at the desired level. The switching noise is usually filtered with an inductor and a capacitor. One method measures the output voltage. When it is lower than the desired voltage, it turns on the switch. When the output voltage is above the desired voltage, it turns off the switch. Audio effects and amplification. PWM is sometimes used in sound synthesis, in particular subtractive synthesis, as it gives a sound effect similar to chorus or slightly detuned oscillators played together. The ratio between the high and low level is typically modulated with a low-frequency oscillator. In addition, varying the duty cycle of a pulse waveform in a subtractive synthesis instrument creates useful timbral variations. Some synthesizers have a duty cycle trimmer for their square wave outputs, and that trimmer can be set by ear. The 50% point was distinctive, because even-numbered harmonics essentially disappear at 50%. Pulse waves, usually 50%, 25%, and 12.5%, make up the soundtracks of classic video games. A new class of audio amplifiers based on the PWM principle is becoming popular. Called Class D amplifiers, they produce a PWM equivalent of the analog input signal which is fed to the loudspeaker via a suitable filter network to block the carrier and recover the original audio. These amplifiers are characterized by very good efficiency figures and compact size, lightweight for large power outputs. For a few decades, Industrial and military PWM amplifiers have been in common use, often for driving servo motors. Field gradient coils in MRI machines are driven by relatively high-power PWM amplifiers. Historically, a crude form of PWM has been used to play back PCM digital sound on the PC speaker, which is driven by only two voltage levels, typically 0V and 5V. By carefully timing the duration of the pulses, and by relying on the speaker's physical filtering properties, it was possible to obtain an approximate playback of mono PCM samples, although at a very low quality, and with greatly varying results between implementations. In more recent times, the direct stream digital sound encoding method was introduced, which uses a generalized form of pulse width modulation called pulse density modulation, at a high enough sampling rate to cover the whole acoustic frequencies range with sufficient fidelity. This method is used in the SACD format, and reproduction of the encoded audio signal is essentially similar to the method used in Class D amplifiers. Electrical SPWM signals are used in microinverter design. These switching signals are fed to the FETs that are used in the device. The device's efficiency depends on the harmonic content of the PWM signal. There is much research on eliminating unwanted harmonics and improving the fundamental strength, some of which involves using a modified carrier signal instead of a classic sawtooth signal in order to decrease power losses and improve efficiency. Another common application is in robotics, where PWM signals are used to control the speed of the robot by controlling the motors. See also, delta sigma modulation, pulse amplitude modulation, pulse code modulation, pulse density modulation, pulse position modulation, radio control, RC servo, sliding mode control, produces smooth behavior by way of discontinuous switching in systems, space vector modulation, Class D amplifier, references. External links, an introduction to delta sigma converters, introductory tutorial on PWM and quadrature encoding, pulse width modulation using 555 timer, pulse width modulation in PID control loop, free simulator.